Greetings, everyone. This is Tianming Liu from Monash University and Huazhong University of Science and Technology. I'm honored to have this opportunity to present our paper, exploring covert third-party identifiers through external storage in the Android new era. User tracking identifier plays a vital role in the mobile ecosystem. Different apps within the same device each collect scattered pieces of information about the same user. And with the help of device identifiers, these pieces are put together to collectively build a user profile, which is then used for many important services, such as personalized user experience and targeted advertising. As privacy concerns mounted over the years, the Android system is implementing more and more restrictions on identifier. Before Android 6, any app can access hardware identifier, which are like fingerprint to the device, would not even change after a system reset. Therefore, stable user tracking can be easily achieved back in the days, but they become available since Android 10. Now, the only available identifier is the Google Advertising ID, which is a unique ID that the user can easily reset or opt out of, which effectively prevents its usage for stable user tracking. So this work is interested in that. In such a new era, are there any attempt to circumvent these restrictions for profit? This study is conducted because we are playing with one of testing devices. We came across some unusual files within the hidden directories on external storage. Here I need to mention that Android storage are divided into internal and external storage. Each app has its own internal storage folders, accessible only by itself, while external storage is shared and accessible by all apps. Upon our further investigation, we found these files stored the identifier generated by an SDK belonging to a Chinese tech giant, which is also one of the biggest internet companies in the world. We also uncovered this SDK's identifier processing procedure. The SDK first tries to obtain an identifier from 3 locations in order, including external storage. After each attempt, the SDK checks if it has successfully obtained a valid identifier. If failing to obtain one from any of the 3 locations, it generates a new one with a random value and tries to synchronize it to the above 3 locations. As the first 2 locations are not accessible to other regular apps, the primary identifier storage and sharing location for this SDK is the external storage. Allow me to further explain the process of user tracking here, which essentially is user identification across apps. This SDK is used within a large number of apps and want to put scattered pieces of information about the same person together by knowing which pieces come from the same device. For this case here, when the first app with this SDK is used on a new device, it will not find any identifier. Hence, it will generate a new one with a random but unique value and store it on external storage. After that, when other apps with the same SDK are used again on this device, it can recognize this device by accessing this pre-existing identifier. Therefore, this self-generated identifier served an effect similar to hardware identifiers, that is to facilitate the cross-app user identification. So what are the security impact of such user tracking? Firstly, and obviously, it infringes upon users' privacy choices. Such tracking went completely behind users' back, and users have no say in this. It also breaches app market regulations that generally demand their apps to exclusively use advertising ID for tracking. Secondly, it also opens doors to potential attacks, because if the identifier is not properly protected, anyone can steal or modify it with ease. We think of 2 potential attacks here. The first is to steal the victim's identifier and use it on the attacker's device. The attacker can then receive advertisements personalized to the victim to infer about the victim's privacy information. Such attack has already been proven feasible by previous literature. The second is that the attacker directly modify the identifier on the victim's device. As a result, the victim is receiving the attacker's ads. The attacker could craft their identifier for political agenda or promoting their own ads for profit. Therefore, we intend to perform a large-scale investigation to explore this phenomenon systematically. To this end, we devise an analysis pipeline that takes a large set of apps as input, automatically random one by one, while using kernel-level instrumentation to report all file operations. Then use heuristics to identify candidate files that could possibly store these identifiers. We then use radar to hook file operation APIs, get their call stacks, and obtain the corporate app component that is responsible for accessing these candidate files. And finally, we analyze the corporate component, which generally is an SDK, to understand how this identifier is generated, stored, and not secured. We have customized the Linux kernel and integrated it into the Android system to comprehensively capture every file operation performed by each app. Due to time constraint, we skip the technical details here, which can be referred to in our paper. Our input dataset contains 8,000 popular apps from Google Play and other third-party markets. Each app is run for 5 minutes, one by one automatically. And we collect all file operations during the run for the next module. Now, in order to find the file candidates that could possibly contain such identifiers, we apply a set of heuristics on the recorded file operations. There are 3 heuristics. The first is about the file location. The identifier file should be easily accessible by all apps. Therefore, it should be in external storage. The second, that it should be relatively stable. Therefore, there should be no frequent deletion in our record. The third one, and the most important one, is that in order to facilitate cross-app user identification, in our large-scale experiment, the identifier file should be accessed by multiple different apps. As a result, we got 30 file candidates differentiated by their file paths. Then is the candidate attributing to find the corporate app component that access the candidate file. We achieve this by rerun a small set of apps, hooking the file operation with Frida to obtain their call stack. Here, our hooking module captured the API file init, is accessing one of our candidate files. We then obtain the call stack of this file init call and locate the corporate component that initiated this call, which belongs to the package of com.qq.e, and advertising SDK belongs to another tag giant. Finally, we reverse engineer the corporate SDK and manually analyze the decompiled code. We examine how the identifier is stored, generated, and still secured, focusing on its confidentiality in terms of whether and how the identifier is encrypted, and the identifier's integrity, as in how the SDK checks the identifier's validity before using it. Then I'll briefly introduce our experimental result. We have collected over 500,000 file operations for 8,000 apps and found 30 file candidates, and 24 are confirmed to contain identifier. These 24 file candidates belongs to 17 SDKs, and many of them are under the name of tech giant. In total, 40% of apps in our dataset included at least one of these 17 SDKs. These apps' cumulative app downloads is an astonishing 100 billion, sorry. Next, I will share some interesting findings. 13 of the 17 SDKs use hidden files to avoid being noticed. One, in particular, gives itself a suffix of database file and hide among hundreds of database files. Another even attach its identifier to a user-generated screenshot, inserting the identifier data to the end of the image file. In terms of generation, they either use a random but unique value, or first try to access a hardware identifier and use random value if failed. As for confidentiality, 8 SDKs store plain text, while others use encryption, but they all use secret keys hard-coded within the SDK. So it is also vulnerable to deliberate attackers who can read the compiled code. In terms of integrity, 7 have no validity check whatsoever. 6 only perform format check to avoid file corruption. The remaining few use hash check. But the hash is also within the identifier files, so they're also vulnerable to deliberate attackers. There are also some other interesting and dangerous discoveries. For instance, we found a popular location SDK sharing encrypted device longitude and latitude data through external storage. We also caught other apps that also use this SDK, but was not granted location permission by user. But they are accessing this file for location, which means any attacker with this knowledge can also do the same. We also discussed in detail about the implementations of these identifiers, especially since a security mechanism on Android external storage called scope storage is introduced. We also reported all our findings to Google, including a post-scope storage exploit, and received their acknowledgement. We also addressed the mitigation strategies. Due to time constraint, we skip this part for now. Please refer to our paper for details. In conclusion, we highlighted the phenomenon of covert third-party user tracking through external storage, developed an analysis pipeline to investigate such practice, provides an analysis of 17 discovered SDKs, and investigated their implication. Thank you all for listening. I'm happy to take your questions.